So in section 11.10, we talked about Taylor's theorem, and we used it to approximate polynomials. So our Taylor series polynomial of degree n, because sometimes it's tough to go all the way up to infinity with these things. So our Taylor series polynomial of degree n would be n equals 0 to, well, maybe I should use a different index. Let me put it in k here. K equals 0 to n, so I'm just using the first n terms. It's going to be fn at some point a over n factorial, or k factorial. I should be putting k's in here. Sorry, it's just a habit of using n's. K factorial times x minus a to the nth power. Kth power, God, sorry. Man, that's just the first n terms in a Taylor series, and a lot of times you use that to approximate a function. And if that's true, that's great. But the difference between the function and its Taylor series all the way up to n is your remainder term. So this is your remainder. That's how much error you're making when you make an approximation. So there's 3 different ways you can get a handle on that error. So one of them is to look at a computer or a graphing calculator, etc., and just kind of estimate this by looking at the graph. That's one way. Another way is if you happen to have an alternating series. So if you have an alternating series, then this error is less than the first term that you leave off. So the absolute value of r sub n of x is going to be less than or equal to the absolute value of the first term you leave off, which is going to be t sub n plus 1 of x. So it's going to be less than that first term. And then you might have to play around with some interval. The last thing that we could do is look at Taylor's inequality. So Taylor had an inequality for the maximum error. And in this case, what you would have to do is you'd have to have a bound for the n plus first derivative, and that bound is going to be m. Then the remainder is going to be less than m divided by, essentially it's kind of like the next term in the Taylor series, n plus 1 factorial, x minus a to the nth power in absolute value, where a is in some interval near, or so where x is in some interval near where you're centered at. So as an example of that, if I wanted you to approximate the function cube root of x near a equal 8, and then figure out, what's the maximum error that we can make, then it's going to look something like this. We first of all find the first few terms in Taylor's series. And then come up with a Taylor series polynomial of degree 2. So that's this right here. There's your Taylor series polynomial of degree 2. Now for your approximation of the error, then it's going to look like this. The error is going to be less than the maximum of the third derivative in some interval around our center, and then we'll divide by this term and multiply by that term. Plugging a few things in here. Let's see. There's our remainder term for n equal 2. We have to first of all figure out, well, what's the maximum of the third derivative near x equal 8, and that maximum is going to occur when you plug in the lower limit from this interval, so from 7 to 9. If you plug in that lower limit, you're going to get a maximum error of about 1 over 7 to the 8 thirds, so kind of small there. Plugging that into our term and taking the maximum on the other end, when x equals 9, you get a maximum error of about 0.004. So a lot of extra work here. And if I wanted to teach this course at a really mean level, I'd be asking you to do this stuff. But I think you know me better. I'm not going to go through this. I did mention this, so you have seen it. That is one way to try and approximate the error in terms of a Taylor series polynomial, the maximum error. But the next way is the one that I really want you to at least be able to do for me on an exam or a quiz. So if you followed this, great. If you didn't, then let's take a look at this next one, which is a little bit more realistic and something that I expect you to be able to do on a quiz. So, let's take a look at example B. We're going to estimate the arctan of x squared from 0 to 1/2. And, oops, let me get rid of this. So first things first, we need to figure out what the arctan, the series is for the arctan of x squared, because there's just no antiderivative for this function. We can't find the antiderivative and just do it that way. So let's go back to our work from section 1110. We had a series there. Here's your series for the arctan. Now, like I mentioned earlier, I really only expect you to pretty much know these series. These three in particular, this one's kind of like, yeah, you should know that one as well. But these three for sure. But the arctan series, that's not something I expect people to have off the top of their head. So let's just copy it down for ourselves. So arctan of x is the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So there's your series. If I wanted a series for arctan of x squared, I can do that. So the series for arctan of x squared, I'm going to be plugging in x squared in here. So it's going to be the sum from n equals 0 to infinity of -1 to the n, and then, sorry about the crampness here, x squared to the 2n plus 1 over 2n plus 1 factorial, like that. You know, I think I am going to have to figure out something about this license thing here. So I want to be able to show this to you. SmartView, launch sign in.
Professor,
Yeah.
is the handout missing a factorial term in the bottom, or we are putting an extra factorial in our example?
Yeah, 1 second here. Invalid username, password. This is so annoying.
If you try signing in with Google, it might put you through your details.
Let's see. No. Signing success. Ha. All right, come on. All right. Let's see if this works. Ah, thank goodness. All right, good deal. All right, so go ahead. Liz? Or no, Sophia? Somebody had a question? Yes.
Yeah, in the handout, the arctangent doesn't have a factorial in the bottom, but you did.
I think you're right. Let's just take a look here. No, I think you're right. Yeah, there's no factorial there. Okay. There is one last thing we need to do here, and that is simplify this term. What's going to happen with these exponents? What am I going to end up with when I remove the parentheses there? -1 to the n over 2n plus 1. What power of x am I going to have? What happens with these exponents? The add, subtract, multiply, or divide? Multiply. So what's the exponent going to be up here? 4n plus 2. Thank you for distributing. Nice. So 4n plus 2. So it's this term that we need to integrate. So let's see if we can't do that. So the integral from 0 to 0.5 of the arctan of x squared is going to be the same as the integral from 0 to 0.5 of this summation. So it's going to be the sum from n equals 0 to infinity of -1 to the n x to the 4n plus 2 over 2n plus 1 dx. So all I'm doing is substituting in for our infinite series there. And now I think you've seen this trick before here, right? What's coming next? Let's see. Well, we're integrating with respect to x, right? So everything that doesn't involve an x can come out. And this summation, well, that's just adding, so the operations can be commutative. Linear, the integral is linear in its properties. So I can rewrite this as the sum from n equals 0 to infinity. Let's see all the stuff that can come out here. I've got -1 to the n over 2n plus 1. I think that's it, right? That's plenty, though. Times the integral from 0 to 0.5 of x to the 4n plus 2 dx. All right, looking good. What's the antiderivative of that?
X to the 4n plus 3 over 4n plus 3?
Yes, nice, well done. Thank you, Ethan. So this is going to be then 0 to 0.5 of x to the 4n plus 3 over 4n plus 3. Now that n plus 3 term can come out here. The 4n plus 3 term can come out here because that's really a constant. We're only worried about the x. So this is now the sum from n equals 0 to infinity, -1 to the n, times 2n plus 1, times 1 over 4n plus 3. And now I can evaluate this function at those two limits. So it's going to look like this. It's going to be 1/2 to the 4n plus 3 minus 0 to the 4n plus 3. And of course that term just disappears. So you're left with 1 over 2n to the, or 1 over 2 to the 4n plus 3 in the denominator. So let's clean this all up. N equals 0 to infinity of -1 to the n over 2n plus 1 times 4n plus 3 times 2 to the 4n plus 3. I just took that term down here into the denominator. It would probably ruin your weekend if I asked you to sum this up, right?
Yeah.
Sum to infinity might take a while. But there's one thing about this that kind of saves our bacon. This is an alternating series with a decreasing sequence. So that means if I approximate this series, the error in our approximation is going to be less than the first term we leave off. So if I do S sub n, let's call this S. That's the exact sum. S sub n is going to be the sum from k equals 0 to n of negative 1 to the k over 2k plus 1, 4k plus 3, and 2 to the 4k plus 3. This is an approximation to this. How good is it? What's our error? Error is going to be the difference between the true value and the first n terms. And this error is going to be less than the first term we leave off. First term omitted. So what we have to do is we have to figure out at what point, that first term that we omit is less than a certain number. Now in our case, that number is 1/10,000th. So if you wanted this to be accurate to within 1/10,000th, the trick is to find which term gives you something less than 1/10,000th. Now, we're going to make this easier than it looks. All right, because all we're going to do is just keep on trying things until it works. So here's how that's going to look. Take out your graphing calculators. For convenience, I'm going to use x as opposed to an n or a k. I mean, you could use those things, but I think it's certainly much easier if we do that. I'm not going to worry about the -1. That comes out because of the absolute value. So all I'm going to worry about is these terms in the denominator. So I'm going to put 1 over all of this. So there's a lot of ways you could write this. Let's see. I'm just going to put it all in one big parenthesis and then raise that to the negative first power. So parenthesis and then another parenthesis, 2x plus 1, right parenthesis, then left parenthesis, 4x plus 3, right parenthesis, left parenthesis. Actually, didn't really need that. Oh, awesome. That's all right. 2 raised to the 4x plus 3. Right arrow to get out of the exponent, parenthesis, another one to close off this term. And because I want it in the denominator, I'm going to raise it to the negative first power. So, wow, a lot going on there. Fortunately for us, we don't actually have to plug in those values ourselves. We're just going to get a table to do our dirty work for us. Now, I hope that everyone's got their table settings still saved from earlier this semester, but I'll just take a quick peek at it for you. Second, and then window. Independent should be set to ask, and dependent should be set to auto. If those settings are great, then go ahead and hit the second key and then the graph key to go to your table. Let me just delete all these things. And now we're just going to keep on typing in numbers until we get something less than 1/10,000th. Now just kind of a quick little word here about 1/10,000th. Starting at 3 leading zeros, 1 over 10,000 is 0.0001. Your calculator regards this as a cutoff, I think. It's going to regard this as 1e negative 4. So when you're doing your work, and you want to try and find an error term, or you want to figure out how many terms until you get something less than 1/10,000th, you want a number smaller than this. So you want this to be a -5. That would be something smaller than 1/10,000th. So let's see how many terms we have to go until we get something like that. So first term, wow, look at that. You're really close with one term. Well, with n equal 1. Wow, look at that. Actually, no, I should have pushed a 2 here. 2 terms. Wow, that's pretty outstanding. With just, the constant term and one more term, we can get an answer that's accurate to within 1/10,000th with just two terms from the sequence, the first term and the k equals 1 term. So that's pretty special. Let's figure out what those terms are, figure out our approximation. So let's pick it up here. Since the k equal 2 term is less than 1/10,000th, you can use k equals 0 and k equal 1 to approximate. And I'm sorry, my pens just seem to be dying on me. So if we're going to do that, let's take a look at what the k equal 0 term and k equal 1 term are going to be. K equals 0, k equal 1. I'm kind of feeling a little bit lazy here. I mean, it's not too hard to plug in a 0 here. K equals 0, you're going to get this to the 0 power, so I'm going to get 1 over, well, if I put in a 0 there, I'll get 1 times 3 times 2 to the third. 1 times 3 times 2 to the third. So that's my k equal 0 term. For k equal 1 term, I'm going to get a little bit lazy here. Actually, lazy is a harsh word. Let's call it economy of movement. Let's get rid of that -1 in the exponent. If I just delete that, can I get rid of that? Yeah, there you go. If I just delete that and then put in a 1, there you go. So let's just do both of them, 0 and 1. So that matches what we got. So we got 1 over 24 and 1 over 2,688. Now there is a change of sign in there. So it's 1 over 24 minus 1 over 2,688. Now I don't really care about the getting a common denominator and all that stuff. Let's just find a numerical value for those things. So 1 over 24 minus 1 over 2,688. Now, this gives me a nice fraction. That's really wonderful, but I actually want a decimal value. So go to the math key and press the second option, something I don't use very often, but there's your decimal value. Can anyone think of a way I can check this? Is there a way I can check this to see just how good we did? Yeah, math 9, right? So let's check this. Now, the unfortunate part about math 9 is that there's no arctan built into our calculator. What do you have to do to get the arctan instead? Inverse tangent. Yeah, there you go. So 0 to 0.5. And then we'll do the arctan as the inverse tangent of x squared and dx. Make sure your calculator is in radian mode. Look at that. That's really close. With just two terms out of the right sequence, we got an amazingly close polynomial. If you subtract these two, so if I go up to here, minus my previous answer, I'm going to get a really small number. Wow, that's pretty outstanding. Comments or thoughts on this one here?
What would our final answer would be that 0.41?
Yeah, your final answer for this one is 0.413. So approximately 3. So yeah, that's just amazing that we can get that accuracy with such a small number of terms there from our sequence. So there are a couple different ways you can find the error in these things. That's one of them, and that's something that I would expect you to be able to do. Negotiate. Okay. Any other comments or thoughts on that one? Let's take a look at one last thing. You don't need to necessarily take notes on this, but it is kind of on the cool side. Does anyone know the formula in Newtonian physics for kinetic energy? What's your kinetic energy? 1/2 mv squared, right? That's our kinetic energy. 1/2 mv squared. There's your kinetic energy. Great. Now, Isaac Newton derived a formula for that, but here's another look at this, in as much as we're in Einstein's universe, no longer necessarily just Newtonian physics. So, for Einstein, we had this little, I want to call it Lorentz. I can't remember what this is called. Anyways, we got this function gamma, which is 1 over 1 minus the square root of, 1 over 1, 1 over the square root of 1 minus v squared over c. C is the speed of light, and speed of light is about 3 times 10 to the 8th meters per second. It's just blazingly fast. You need a car that fast to beat the traffic to work. Kinetic energy is the difference between your energy and your energy at rest. So if I factor out the mc squared from this, then I get 1 minus, or gamma minus 1. Now gamma is this term right here. So it's just a rewriting of this one. This can be rewritten as 1 minus v squared over c squared to the negative 1/2 power, which is exactly what we did down here. And for this, we've got another series. This is the binomial series. Now, this is something that Isaac Newton discovered when he was working by himself in his family farm in Woolsthorpe during the plague years of 1665 and 1664. His annus mirabilis, his miracle year. One of the things he discovered was that the binomial formula for which you use Pascal's triangle, all right, this can actually be interpolated to be an infinite series and doesn't have to be an integer, and you get some approximation like this. Well, we're going to use that approximation with this thing here for x. That term is going to be our x. Now, a quick little note about that term. This term is going to be pretty small when you're dealing with speeds that we would experience. Nonetheless, the approximation is going to be gamma is approximately this series. I'm using n equal 1/2, negative 1/2 for that. If we look at this series, anything past the second term here is really going to get small. How small? Well, let's think about a car going really fast. Think of NASCAR. 100 meters per second is around 224 miles per hour. Sounds pretty fast, right? Not compared to the speed of light, which is 3 times 10 to the 8th. That gives you this term. If you square that, which we have to in our formula, you get a really tiny number. There's 12 zeros in front of this number, so it's really tiny. And what this is it's just kind of a fancy way of justifying the fact that, you know what, after this term, these terms get incredibly small, and we're going to leave them off. So we're just going to approximate gamma with the first 2 terms here. Substituting in, you get mc squared times gamma minus 1. Well, gamma minus 1, gamma we're going to approximate with this, so that 1 cancels out. mc squared, the c squareds cancel each other out. You're left with 1/2 mv squared for your formula for kinetic energy. So when your speeds are really slow, relatively slow, Einstein's theory reduces to the theory that you got for Newtonian physics. So, wow, pretty cool stuff. And it's just from the binomial series. I keep on looking for that. It was one of our handouts, but I'm not finding it in my stuff here at the moment. Anyways, that'll do it. That'll do it. Comments or thoughts? All right.